Mhm. Okay, it looks like. Are we here? Are we here? Have we started the show? Yay! All right. Thank you for that Q identity 4. So, without any further ado, we shall start the show in 3, 2. This is TWIS. This Week in Science, episode number 721, recorded on Wednesday, May 15th, 2019. Understanding Antarctic Ice. Hey everyone, I'm Dr. Kiki, and tonight on the show, we are going to fill your head with the moon, sticky Scandinavians, and STDs. But first,
I was not prepared. I was definitely not prepared for this.
Kiki broke Justin.
right off the bat. Woo! There we go.
Okay. I can recover. I must. Disclaimer. When wandering through the world, take note, because everything you see is noteworthy in some way. Yes, there is too much information all at once to pay attention to everything. But eventually, you may find yourself focusing in on something of interest. And if you pursue this interest, it can, with time and study, make you an expert on the subject. This, of course, does not mean you will know it all, but your knowledge will not be alone. An ecologist might not know much about psychology, but know a great deal about the woodland creatures that inhabit the forest. The geologist may not see the forest for the trees, but have insights onto the history of the region and the dynamics of the dirt beneath the roots and leaves. If the astronomer seems moody on a sunny day, it's just because they're waiting impatiently for a better view of the Milky Way. The physicist can appear an unlikely sort of explorer, staying inside, hunched over a keyboard, eyes glued to a screen for several hours. But they might be adventuring anywhere, from the Big Bang to the tiniest traces of subatomic particles escaping a super collider. And while the psychologist might not know much about quantum microgravity, they might understand ways in which the ecologist might better communicate to their spouse. And at some point, when enough of us have pursued our interest to the point of expertise, we can share our insights with each other. And when that day comes, we will all know more about the world around us than any one of us had time to take notice of alone. Because we are never alone, as long as we have This Week in Science coming up next.
I've got the kind of mind that can't get enough. I want to learn everything. I want to fill it all up with new discoveries that happen every day of the week. There's only one place to go to find the knowledge I seek. I want to know what's happening. What's happening? What's happening this week in science? What's happening? What's happening? What's happening this week in science?
Good science to you, Kiki and Blair.
And a good science to you too, Justin, Blair, and everyone out there. Welcome to another episode of This Week in Science. That's right, TWIS is back once again. More science in our little science grab bag of fun. We're here to talk with each other and with you about it all. So I hope you're ready for a great show. We have a bunch of fun stories ahead and an interview about Antarctic ice. It's going to be amazing. I have stories about the moon, whale genes, and Justin, what do you have for us?
I've got more ancient-y Neander news flashes, a sticky Scandinavian situation, and why slow might kill you faster than speed.
Oh, that I would like to know. Blair, Animal Corner, what's in there?
I have the aforementioned STDs. No, you can't wait for those. I have test bias in animals, and I have catapulting spiders.
Catapulting spiders. Oh, more fun with spiders for all of you spider files out there. All right. As we jump into the show, I would love to remind you that if you have not yet subscribed, It's not so hard to do. You can find us on YouTube. You can also find us at twis.org for information. You can also find us any good place that good podcasts are found. All right, so now let's dive into our interview. I would love to introduce our guest, Dr. Christina Hulbe. Dr. Hulbe is a geophysicist who studies how and why polar ice sheets change over time. She's professor and dean of surveying at the University of Otago in New Zealand and the program lead for an investigation into the vulnerability of the Ross Ice Shelf in West Antarctica to the influences of a warming world. Dr. Hulbe, thank you so much for joining us.
Tēnā koutou katoa. Hello, everybody. Namihi o te po. Good evening.
Oh, I love that. Yes. You are joining us from New Zealand. So for yourself, it is it's daytime, right? You're how far
It's
apart
a rainy
are we?
afternoon.
Rainy
It's a
afternoon.
rainy afternoon.
As we
Just
start.
perfect. We're getting a storm from the Southern Ocean, so I'm very happy.
Oh, nice.
Just like Antarctica is right here.
Yes, it's being brought to you by the winds, the waters and the
Coming for a
winds.
visit.
So I would love to know, I mean, Antarctica is this distant, far off continent that very few people on this planet ever get to visit, and yet it is a focus of your study. When did you first travel to Antarctica and why?
My first trip was in 1991. I like to say that in front of classes because most of my students weren't born then, so it's kind of exciting. I'm very old. And I went there as a master's student, actually. I did geological engineering as an undergraduate, and when I thought about what kinds of jobs you could get as a geological engineer, I thought, oh, I don't want to do mineral extraction necessarily. I don't want to build dams. I think I need to stay in school for a while. And when I would study as an undergraduate, I'd go sit in the stacks in the library way back in a quiet place. And the books that were along the shelves where I sat were the bound editions of the Journal of Glaciology. And when I needed a break, I'd pull one off the shelf and I'd have a read. And it turned out that it was all about physics, which I loved, and mountains, which I loved. And I thought, okay, I'll do that. And the only way I knew anything about it was that I happened to read a book. And yeah,
just the one that happened to be right near you. I'll just read about glaciers. Yeah. Let's do this.
Why not? Okay. Well, I learned about glaciers, in my geology classes, but like what glaciology, the study of the physics of ice and how it moves and why it changes, and it was just a really interesting world. And of course, where I work now, there are no mountains at all, but there's a lot of ice.
There is a lot of ice, but so has Antarctica, there are glaciers all over the planet. Why did Antarctica end up being the place?
For me.
For you.
Because the questions are really big and the questions are global. And it was a place where I had the opportunity to define a project that was all my own. And I could see what a question might be. I could figure out how to answer it. And the person that I ended up working with for my master's degree, Ian Willens at Ohio State, when I went to visit him, when you're just starting out and you go and visit schools and think about where you might like to work. When I went to meet Ian, he took me for a walk in the woods with his son. And we talked about every single thing that we saw along the way, why the leaves were the way they were, why the stream was flowing the way it was. And I thought, right, this is where I want to be. And that was what it was like working with him. Everything was an interesting question.
That is that's just the way to approach science, right? How many questions can you ask about the world, and then, can you figure out how to actually answer those questions?
Yeah, and also just being in the presence of a really observant person, I've noticed it can be very inspiring. I've met a few of these individuals in my life, and they always just amaze me about how much I'm missing on a simple walk. Yeah.
Yeah, absolutely.
I'd love to know about the continent of Antarctica. I mean, When we think of Antarctica, we think of the ice. So obviously the study of the ice would be important there, but there's more to it than that. So can you give us a little introduction into the I guess the geology of Antarctica, or what the continent really consists of?
Sure. So Antarctica has been, well, it's plate tectonics, right? So plates move apart, they come back together. There's some of the very oldest continental crust on the Earth underneath the ice in Antarctica. My favorite past continent, Rodinia, is underneath there in East Antarctica. But so Antarctica has been isolated from sort of the rest of the world for a while, for millions of years. And like, as that happened, as it became isolated, the ocean around Antarctica became one continuous ocean, the Southern Ocean. So the wind blows all the way around, the westerly wind blows all the way around the continent, and underneath that, the ocean circulates all the way around the continent. And that really isolates it, and that's setting it up that way kind of helped Antarctica to start to get cold. And once it started to get cold and glaciers and ice caps start to grow, then they're kind of changing the color of the surface of the Earth from kind of dark rocks to bright white surface. And that bright white surface reflects a lot of the incoming solar radiation rather than absorbing it all. And that helps things get colder. So you start to get these kind of positive feedbacks that allow Antarctica to get colder and colder and colder. And over, tens of millions of years, sort of really the last 30 million years, ice sheets start to grow bigger and bigger on Antarctica. And when we look at it today, we divide it into kind of two parts of the continent, East Antarctica and West Antarctica. And there's a mountain chain that runs through most of the middle of it, of the Transantarctic Mountains. And the rocks underneath the East Antarctic part and the West Antarctic part are very different. The East Antarctica underneath there, it's like old continental crust, like Canada. Underneath West Antarctica, it's much younger. It's a former like Rift Valley, like the East African Rift Valley. Huh. And the different underlying geology means that the way the ice sheets grow on top and the way the ice flows is different in the two parts. And where I work in West Antarctica, the crust underneath the ice is thinner. The elevation of the Earth's surface, or the bathymetry, the seafloor surface underneath the ice sheet, is much lower. So if you took all the ice off of Antarctica, a lot of East Antarctica, you just see rocks, just like we do in Canada today. If you took the ice off of West Antarctica, it would be ocean. And so those differences mean that the ice sheets in the two parts of Antarctica behave in really different ways. And with a lot of the work that I do, thinking about how processes operate today and how we can use kind of ice process understanding, ice flow understanding to make projections about the future, those differences are really important because they mean that West Antarctica is a lot more vulnerable to change. And I guess a kind of a really simple way to think of it is, Antarctica is the largest source of sea level rise, right, on Earth today. As we continue to warm up and Antarctic ice melts, there's 50 meters of sea level equivalent there if we just melted it all and spread it across the ocean. So it's the largest source of future sea level rise. West Antarctica is the largest source of uncertainty in the sea level rise projection. So trying to understand West Antarctica better sort of has a direct bearing on our ability as scientists, as glaciologists, to say useful things for society.
When we're looking at the ice, I mean, there's this big the discussion about the ice that actually contributes to sea level rise. It's ice sheets that you're talking about. This is ice that is over the ocean and not over land, correct?
So the ice sheet is resting on land.
Okay.
So if you think about how we make an ice sheet in West Antarctica, so glaciers start to form as the planet cools. little ice caps start to form high in the mountains. And as things get colder, those grow. The ice flows like a really thick fluid, or you could think of it as a rock that's really close to its melt temperature. It flows just like a really thick fluid would, down its own surface slope, down toward the sea. And as it gets thicker, it can extend into the sea. And so it can kind of push out and displace the ocean water and fill up that ocean basin. And that's what happened in West Antarctica. But if the ice is like resting on the Earth's surface, it's like its own reservoir of water, right? So you took water out of the ocean and you've stored it in the ice sheet. As the ice continues to flow, it speeds up as it goes from the center toward the edge. As it speeds up, it stretches out, so it gets thinner, and eventually it gets thin enough that it does go afloat on the ocean. And then we call it an ice shelf.
Okay.
So we have grounded ice sheet, floating ice shelf.
Got it. And we've seen with climate change and warming that's already occurring, and also just natural processes of erosion at the edges of the ice shelf. We've seen the calving of very large chunks of ice that people have equated to the size of eastern seaboard states.
There's always something.
As they go floating off into the ocean. But let's talk about this process of the movement of the ice and the flow of the ice. I'd love to find out more from your perspective as a geophysicist. Like, what are the forces that you are interested in as, what is controlling the ice movement and what will contribute to stuff down the road?
Sure. So fundamentally, it's all about gravity, right? So it always is.
Yeah.
Unavoidable gravity. But so as you grow an ice sheet, if you think about, you're making kind of like a pillow of ice or a dome of ice. So it's the surface height is different in different places, right? It's high in the middle and it's lower in the edges. If you made a slice through that ice sheet and you took like a fixed level, so if you thought about the gravitational attraction of the Earth and you just made a fixed level, then in the interior of the ice sheet, the sort of column of ice that would be above you at that level is really thick. As you go toward the edge, it's thinner. So if you imagine being a little person down there at some depth in the ice, the weight of the ice above you in the interior is greater than the weight of the ice above you near the edge, or the pressure that you experience is different. So there's a pressure gradient that is generated by the surface slope on the ice. And that pressure gradient, gravity tries to flatten that out, right? And that's what we look at as flow, right? So the ice deforms in response to that pressure gradient. It tries to flatten out that surface slope. Another way to say it would be that the ice is flowing sort of down its own surface slope or in the direction of its own surface slope. So that's all about gravity. How fast it flows depends on a whole bunch of other things. So it depends on the thickness, but it also depends on the temperature of the ice. So the warmer the ice is, the faster it'll deform. The colder it is, the slower it goes. It depends on what's underneath the ice. So if the ice is flowing, if it's resting on bedrock and it's kind of the gravity is causing it to move across that surface, the rocks underneath are kind of rough, right? If you imagine pushing your hand across a granite boulder, it's really rough and it's hard to do, right? So the ice has the same experience. And what happens is that down at the bottom, it doesn't move very much, but as you if you think about like putting a deck of cards on a table and you push across the top of the deck of cards, the ones at the bottom feel the table and they don't move. But the ones up at the top, they're further away and they do move. So the same kind of thing happens in the ice. If the stuff underneath the ice isn't really rough or isn't really strong, if it's smooth, like you have mud down there instead of granite boulders, or if you have water down there, then it can go faster. Mm. So exactly what's underneath matters a whole lot too. And then
it's funny that you said granite boulders, because that's what I understand. There's a lot of giant rounded granite boulders and the Sierra Mountain that are near here. And it's because there was a giant glacier on top of it. And so these were giant, large granite formations that, as a glacier slowly moved across it, created these giant rounded boulders. I mean, the boulders themselves came from having had a glacier on top of them, and sort of doing like you might do in a kid's rock experiment, where you take rough rocks and put it in there, and they get ground around and around. Yeah.
Yeah, their glaciers are very effective at smoothing things out.
Yeah. So you mentioned the the impact of warming, and so we've got warming from the atmosphere that will have impacts on the surface of the ice, and there are lots of complex interactions there. But what about the water underneath? How are you looking at how the water underneath the ice shelf is affecting that movement and the melt?
Absolutely. So if we kind of continue on our conveyor belt of ice from the inside of the ice sheet out to the edge, once the ice gets thin enough to go afloat, like, water is not strong at all, right? It's really weak. It just gets out of the way, and the ice can flow really fast. So it stretches faster and faster, it gets thinner and thinner, and eventually you get to the kind of the front, you calve off icebergs. And for any given sort of climate state, there will be some shape to the ice sheet and ice shelf that's in balance with whatever the ocean temperature is, whatever the atmospheric temperature is, whatever the ocean circulation is like. But when we start to change any of those things, then like the thickness of the ice starts to change, and that means that all the forces change, and that means the flow of the ice changes. And once you start doing that, then that can, you can have feedbacks that propagate through the system. So what we think about right now, what we see happening in some places in Antarctica, is that the temperature of the atmosphere is changing on the Antarctic Peninsula, and that's driving changes in ice shelves and glaciers. Changes in the circulation of the ocean water is changing on the Amundsen Sea side of West Antarctica, and that's causing ice shelves, the floating bits, to melt. And as they do, the forces all change, and the grounded ice sheet starts to flow faster, and that propagates sort of into the interior. Where I'm working right now with this big Ross Ice Shelf project, there hasn't been much change yet. And that makes it actually a really good place to go, because we can look at these processes before they've been pushed. It's a lot harder to understand how things work if you arrive at just as everything is changing.
Right as it's falling apart, you're like, what's going on? What's going wrong? Yeah. Yeah, so I think this is a great opportunity for you to tell us what it's like to go to the Ross Ice Shelf. I mean, in your on your website, you say that you use satellite imaging and all sorts of eyes from the sky to get a look at Antarctica and the ice shelves, but you also go there. So can you tell us about what a typical field season entails going into the Ross Ice Shelf area?
Yeah. It entails a whole lot of planning. And we're already, midway through last year, we were starting to get ready for the trip that we'll be taking this November. And that's just, there's so many parts that you have to sort of get moving in the right direction. And it takes a lot of like logistics support, right? So as a scientist, like, we come up with a good idea, and we pitch our good idea to a funding agency, and hopefully we get some money. And if we get the money, then we start talking with, here in New Zealand, we talk with Antarctica New Zealand, which is the group that owns all the tents and maintains the base on Ross Island, and owns all the snowmobiles and all of that. So we come up with the big plan. We need this many snowmobiles, we need this many tents, whatever it is, collaboratively with their team. When it's finally time to go, we ship our science cargo we send it to Christchurch, which is kind of the base for going to Antarctica. And then either it goes on a ship if we get it together soon enough, and if it's something really big and heavy, or it goes on airplanes. And New Zealand works together with the U.S. Antarctic program to ship equipment and people on planes to Antarctica. So we get to Scott Base. We have a few days of figuring out where all our stuff is and testing it to make sure that it still works. And then we just wait for the weather to be right to go wherever it is we're going. And for this project, we're pretty far away. We're the place we've been working the last few years is about 350 kilometers away from Scott Base. And we have to get there either by driving or by flying. Driving takes longer, but you can drive in most any weather. Flying is more comfortable and faster, but the weather has to be just right. So we sort of work with the logistics experts about how to do that. And, you know, once we're there, where we've been working out on the Ross Ice Shelf, it's really flat. It's really flat because it's floating. But I could say almost all the places that I have been in Antarctica are very flat. Depending on the kind of, just because it's this big, thick layer of really viscous fluid that's trying to flatten itself out, and it's pretty good at that. But, you know, depending on where you work in Antarctica, you might have a completely different kind of mental model of, like, when you hear the word Antarctica, you might think of something totally different. But when I hear the word Antarctica, I think of sort of endless, flat, white, drifting snow. That's where I work.
Yeah. So when you're driving across, how long does that take you? And is it slow going? I mean, when I think of Antarctica and some of the stories I've heard of these, as you go across, there are these crevasses and things that have to be crossed. And how do you do that with your vehicles and your trailers and
carefully? So again, with a lot of planning, right? So we use satellite imagery to kind of plan for the safe routes. And then when we're actually driving, if it's a new route where we haven't gone before, we use radar to look at the subsurface. So we have a team that's out in front with experienced mountaineers who are running a radar system to look out ahead of us to make sure that it's safe to continue. But we also, for this work, there are a couple of tricky places that we have to get through. And we work collaboratively with the US to establish safe routes. And then we follow those safe routes. Like, we're actually not interested in having any adventures at all.
Get there safely and then do your science. And so once you get to your location for your measurements and for the work that you're doing, what are you actually doing there?
So in this project, the big idea is that if we want to understand kind of how this part of Antarctica is going to change in the future, we know that, or if we want to improve the projection that we make about future change for society, that we need to understand rates and we need to understand if there are thresholds in the system. So maybe it works one way for a while and then some threshold is crossed, like it gets just warm enough, or the ocean circulation changes just enough and it starts to work in a different way. And that's never just about one thing. It's always about kind of interactions of different processes. And so we said, if we want to do this right, it has to be interdisciplinary. And so we've got to have oceanography, glaciology, paleoclimate studies, meteorology studies. All of this has got to fit together. And we're not going to let anybody work just on their own thing, right? We're going to ask questions that require people to collaborate. And so, you know, if I want to answer my questions, I have to try to think like an oceanographer, and the oceanographers have to try to think like me. And so that's the big framework. And it's a lot of fun, especially when we're out there in the field and we're making measurements and like the only thing you're thinking about is this project. And like you're never more like in the zone than when you're out in a field camp in the middle of the wilderness, right? All you're doing is trying to do the science right. Or clean the dishes. That's also important. But, you know, you got to do all the daily stuff too. But it's so exciting, you know. And okay, so what are we doing? We are characterizing the area where we're working, that the snow accumulation, what the weather is like. We are using radar to image the interior of the ice, what the ice is like at that site. We use data from satellites to think about where the ice at that site came from, what's happened to it along the way. And then we're using hot water to drill through the ice. So we make a borehole about as large as it gets, is about 30 centimeters in diameter. And we do that so that we can look at the ocean underneath. So we're interested in the ocean circulation underneath the ice shelf. It's, you know, it's an ocean the size of the North Sea, and it's been observed sort of once in one place back in the 1970s, and then a little bit right out toward the front of the ice shelf. So it's a huge, completely unobserved, unstudied part of the world ocean. And we're making this tiny little kind of pinprick down through the ice shelf and looking at our one little spot, and immediately, like sort of infinitely increasing the amount that's known. So we send instruments down to measure what the water is like, the temperature, the salinity. We can measure the current speed. We can measure how turbulent the water is. And we profile up and down in the ocean. So at the site where we're working right now, the ice shelf is about 360 meters thick. And then there's another 400 or so meters of ocean beneath that. So we're floating over the ocean with the seabed down underneath us. So we have a look at the water repeatedly. And then we also are sampling the sediments on the seafloor. And we want to do that so that we can try to build a record of what's happened here in the past. So, you know, as you know, if you're in the bottom of a lake or in the bottom of the ocean, over time, fine particles settle out of the water and collect on the sea floor or on the lake bottom. And as they do that, they record environmental conditions at the time that they settled out. And so what we do is use a tool. The one we had the most success with a couple of years ago is a thing called a gravity core. Again, it's all about gravity. And essentially what we do, it's like a plexiglass tube on the end of a really big weight with a mechanism to create a suction on the top of it. And we use a winch to lower that thing down all 700 meters till we're right above the seafloor. And then we let go of the brake on the winch, and it falls down, and the tube sticks into the sediment on the seafloor. That releases the mechanism to create the suction. And then we slowly, carefully pull it back up to the surface and cross our fingers that the suction worked. And if it did, then there will be sediment, layers of sediment in the tube. And then we can use those to kind of look at the past. And
how long does it take to lower it all the way down and then pull it back up? Because it seems like that would be careful work, right?
Indeed it is. So it takes about 45 minutes one way, which it depends on what you're doing. So the oceanographers, if they're making really careful profiles, they may go quite slowly. But if we're just trying to get down to the seafloor, then you can go faster. The trickiest bit, if you think about it, like there's this big ceiling of ice up above, you know, if you're swimming along in the ocean down there, there's a big ceiling of ice up above you. And we've made this tiny little hole, and we've got a rope hanging down. It's a smart rope, but it's a rope hanging down through that tiny little hole. And once we collect the sample, we need to carefully sort of pull it back up and get it back through that tiny little hole. So we monitor the pressure that the tool is experiencing as it comes back up. So we know what depth it's at. And when you get close to the bottom of the ice shelf, then you slow things down so that you can make sure that you get in correctly. And you cross your fingers. And you trust the engineers who built the whole system and knew what they were doing.
In one of your figures here, you have a cross section of seafloor sediments, and across it there are these various layers. Some of them you have pointed out as being places that are called grounding lines and grounding line retreats. What are those exactly?
Sure. So if you think about the kind of conveyor belt of ice going from the interior to the ice shelf and to the coast, that place where the ice goes afloat, gets thin enough to go afloat, we call that the grounding line. And that's like the boundary where the ice or the ocean water that was stored in the ice sheet returns to the sea. Right. So you have evaporation from the ocean, you make snow on the ice sheet. It's just like any other land-based reservoir of water. But when it flows back across the grounding line, it returns to the ocean. So as the grounding line changes position, you're either sort of making a withdrawal from sea level or making a contribution to sea level. So if the grounding line retreats, if it goes back in toward the interior, you're putting more water back into the ocean effectively. And that happens as all the climate conditions and the forces that we were talking about before change. So at this spot, there's now floating ice shelf, but if we go back in time to the last glacial maximum, it would have all been grounded ice. And so if you think about, what was the most recent big warming experiment that Earth went through, it was the warming from the last glaciation. So we want to look at this spot and try to figure out how it fits in the pattern of sort of retreat from, through that last big warming experiment. And a thing that's special about this site, mostly, we look at evidence from the mountains, from the Transantarctic Mountains, places where rocks are exposed, or we look at the seafloor where there isn't any ice. But a lot of the history of Antarctica is underneath the Antarctic ice sheet. It's really hard to get at. So this is a special place because we can actually get the record itself. So
How do you use that record to start to predict what is going to happen in the future? I mean, we see the, IPCC reports and the various possibilities for carbon dioxide concentration. Can you also start to predict what's going to be happening with these ice sheets in various scenarios?
that's what we hope. That's what we told the funders.
Right.
So yeah. One of the big things for us is that, we know that in past warm worlds, there was a lot less ice in West Antarctica, but we don't know how fast those transitions happen. And if we don't know how fast those transitions happen, we can't really test the models that exist today, right? So you can build a model and you can test it by recreating what we know of the record of the past, but there are big gaps. And so this issue of how fast can things really change in West Antarctica, the biggest source of uncertainty in the sea level projection, if we can't really constrain those rates, then there are lots of possible futures, and it's hard to tell one from the other. So the idea is to be able to better constrain rates. But another idea is to figure out which of those processes or process interactions matter the most. So the ocean observations that we've made are causing us to kind of rethink exactly how the circulation underneath the ice shelf works. So it's like a wedge of ocean water underneath the ice shelf. Water comes in, so there's kind of the open Ross Sea out there seaward of the ice shelf, and the water circulating around in the ocean flows underneath the ice shelf. And as it does, it can do some melting, maybe. It can get mixed with other water that's already under there. But almost nothing is known about how any of that actually plays out. And that means that while we can build ocean circulation models that in air quotes simulate that circulation, we don't really have any data to test those simulations.
So you need that data
Yeah, pretty much.
Yeah, there was a study that just came out this week, maybe today, that I found that I thought was really interesting. Researchers from Australia used Argo floats to be able to get data on the water under, in let's see, some
Amory
area.
Ice Shelf,
Yes, and they
probably.
were and they were looking at it during the winter months as well as the summer months to try and get an idea of year round. Have you run into issues with your models and the way you're looking at stuff because you're only able to be there in
We're there
the
all year
summer?
round.
Oh, you
We
are?
left. We left the mooring, so this is even cooler. We So
You're there in the dark of winter?
not me personally. A battery is.
Yeah.
So our little hole in the middle of the big ice shelf with the little string hanging down, there are instruments that are measuring temperature and salinity and the current all the time at a few different depths. So if you imagine that big slab of floating ice, we made our little hole, we dangled some things down through the little hole, we left a few things behind. So we left a series of ocean sensors. The connection to the surface, the wire that goes up to the top, is now frozen in, so it's there forever. There's a battery down there at the bottom, and it's sending a signal back up to an iridium satellite antenna at the surface,
Oh, wow.
and it's sending the data back to Wellington as we speak.
That's
I
amazing.
know. It's so exciting.
It's there forever, you said? How long do the batteries last?
Well, we'll let you know.
How long are you hoping that they will last?
Wow, well, we don't know. I mean, really, this is like nobody's ever done this before, right? So we don't know. A few years is what we're hoping for.
Yeah.
We were
That'd be
excited when we
amazing.
got to a whole year and it was still going.
That is cool.
Yeah, I know.
That's like when you buy light bulbs and you're like, it's still going and I don't have to go to the store and replace the light bulbs or the batteries in your fire detector. It's still working. It's great.
I feel like it's also kind of like a Mars rover.
Yeah.
It's so far
exactly
removed,
like that.
Yeah.
Yeah, in fact, and we have collaborators at Georgia Tech who really care about icy moons, but these places where we work are good analogs for that.
Yeah.
So
That is
they build
cool.
instruments that, they plan to send to space, but they can test them in Antarctica, which is pretty close.
Oh my God.
Right. So if it can survive Antarctica, it could possibly survive Enceladus or one of these icy moons, right?
Yeah.
For your work, I was looking at there's a wonderful you shared a link with me of a TEDx Scott Base talk that you did, and I love the fact that there was a TEDx conference at Scott Base in Antarctica, and that you gave a talk during that conference during that event. But in the talk, you discuss these multiple scenarios of if we were to let the water and the climate warm to a certain extent and looking at the possible outcomes, um, and trying to determine what would happen if we stop processes at different points, how it would change things. I'd love if you could describe your analogy of being parked at the top of a hill.
Yeah, right. So I was talking about work that I did, well, really that was led by a PhD student who worked with me, Scott Weibel, who's in Portland. And the concern was one of these places in West Antarctica that's changing quite quickly right now, and where there might be a threshold beyond which you just can't stop. And the processes that you set in action keep going, and you sort of get the maximum retreat of the grounding line and the maximum withdrawal of water from the ice sheet back into the ocean. But we don't know exactly sort of where in space and time and physics the thresholds are. So we don't know if we really crossed them or not. So what Scott did was build a model of one of these one of these glaciers is changing rapidly now, a computer model, TWIS glacier. And he developed a way to be able to tell from the map, like when that threshold has been crossed. So he set the model up to be as close to the present day as he could. And he then started like pushing as slowly as he could, just kind of gently nudging the whole thing along. And we do that so that when like the transition to runaway retreat starts, you know exactly why it happened. And then you can watch what happens next. And one of the experiments that he did was to say, well, okay, so I can find where that transition is. What happens if I push a little bit harder? Does it make a difference? Or is it just once you make the transition, that's it? And
So
what he
how
found—
long ago did we pass that threshold?
Oh, that's a whole different question. So we're modelers. We don't deal exactly with the real world. We make a lot of simplifications. And in my fare, in my house, we're really interested in the processes more than in the detailed projection. But so the process understanding was that it absolutely does matter how hard you were pushing when you start the instability. So, and it matters how hard you were pushing when you stop. So that kind of the idea is that it's never too late to make a change. So even if we invoke this kind of worst case scenario in West Antarctica and we push into the runaway retreat, if we push less hard when we get there, it's still going to happen, but it'll happen over a longer time. So we have more time to adjust and we have more time to get ready for the change that's ahead. If we're pushing harder when we make that transition, then we have less time to deal with it. It's kind of the big story, right? So the analogy of, it's like the analogy that I use is imagine that you're sort of at the top of a hill with your kids in a car, or the whole world's kids, as it turns out with global warming.
It's a noisy car, but okay.
Yeah, the noisy car. You got to make lots of stops. Yeah. But you need some books, audio books. But you know, it's like if you're starting to head down that hill, and you don't know, you're starting to head down. You don't really know if you've gone over the edge, but you know that if you go over the edge, you're careening down that hill and you're going to crash at the bottom. Like it matters when you put on the brakes, right? If you're going to crash one way or another, if you don't put on the brakes, you're going to be going faster when you crash. And even if you're not sure if you've really made it over the edge or not, it's still a good idea to put on the brakes just in case.
There you go.
That's the analogy.
I love this analogy, and I think everyone should know this analogy because we should put on the brakes now.
Yes, I agree. And it's not even hard.
No.
It's not hard to put on the brakes, right?
Yeah.
Change your diet.
Yeah, and we had a wonderful conversation with Jonathan Foley from Project Drawdown about solutions to climate change, which I think, you know, that's one side of it. And then it's really interesting to talk about these processes that are actually occurring and what we understand and what we don't understand. For, you know, the general person who is not a geophysicist, or
I'm not one.
I know we're not geo.
You could be.
We could be.
Yeah.
What is the from your work? What is I think the one important thing that people should understand about the dynamics that are at play?
I think the most important thing is that it's all connected, right? That what we do here in Dunedin, New Zealand, Ōtepoti, Dunedin, like it matters everywhere, right? It matters in Antarctica, and the change that I do or don't create that changes something in Antarctica changes something about the atmospheric circulation, which then feeds right back to me here in New Zealand or to my grandchildren here in New Zealand. Right. So I think that's the big thing. Antarctica seems remote, but it's not. It's all part of this connected system. And the things I do actually matter.
The things we all do actually matter. Yeah. And do you have any recommendations for for young female scientists who may want to embark on a geophysicist adventure to Antarctica?
It's a great time to be a glaciologist. When I started doing this kind of work, not entirely for happy reasons, but take what you can get. When I started doing this work, you could fit all the people who do what I do in a clown car, and now there are a lot of us, and it's an increasingly diverse community of scientists, and that makes it sort of more fun and more interesting, more worldviews, more ideas about what's most important all the time. So it's just, from the point of view of diversity, glaciology has a long way to go, but it's getting better and better and better. And yeah, come and join us. Help make it better. That's the thing.
I love that. And you have an Instagram channel. So what is your Instagram channel so people can follow you and your Antarctic Ross Shelf Adventures?
So it's a long title. It's the Ross Ice Shelf Program, but it's spelled not in the American way. It's spelled in the New Zealand programmy way. Yeah.
That's how I pronounce it when I read it like that. Yeah.
That's how it looks to me too. I haven't lived here that long. I have to code switch.
Yeah.
Is it a Z or an S or a Z? Could be any of them.
That's right. You have to switch your spell check program depending on which continent you're on, which country you're in. Exactly.
Yep.
Ross Ice Shelf Programmy.
There you go.
Get some
Yeah,
great
so
imagery.
we post there all year long. It gets a little funny sometimes. There'll be some New Zealand native birds in there during the winter when we're not in Antarctica, but we post while we're out in the field as well to kind of keep people up to date with what's going on. So 2 years ago when we were stuck with bad weather and we weren't going anywhere, it kind of got more and more demoralizing, but
And you'll be heading out there again for this next summer field season. Is that
Indeed, in November. Yeah, there you go. New Zealand robin down there, little black robin.
Great. Wonderful. So as of November, there should be some new photos coming from Antarctica, right?
Indeed.
Indeed.
Up to the minute.
Wonderful. Well, Dr. Hulbe, thank you so much for joining us this evening and sharing your work with us and helping us understand the important perspective that it brings to our understanding of our planet.
Hey, Connie Mai. It was great to talk with you.
It's wonderful to talk with you. All right, everybody. You can follow the Ross Ice Shelf Program. We will put the link in our show notes. I will also link to Dr. Hulbe's lab, her profile page at the University of Otago. If you would like to find more information about her work, there are links there. And we are going to take a quick break. We will be back in just a few moments for more This Week in Science.
Can't explain things you've heard more than intuition. A lot of reason shows the way to go. New conclusion. The methods of hypothesis and patience are the only things I need. Put on a pair of goggles and go looking for the things I couldn't see. The answers lie somewhere within this scattered plot.
Thank you for listening to this episode of This Week in Science. We are so glad to be with you for another episode full of science with a wonderful interview this evening. If you are interested in helping TWIS out, listening is one of the best ways that you can do it, but so is sharing TWIS. You can share TWIS.org with people you know to enable them to find more science than they could have ever dreamed of. No, well, find ways that they too can subscribe to TWIS. That's right. At TWIS.org, there is a wonderful orange subscribe button that allows you to easily access YouTube, iTunes, and the Google Play podcast store so that you can subscribe and get our show on your device. So send your friends to twist.org to allow them to subscribe very easily. Other things that you can find at twist.org are our Zazzle store, where you can find wonderful products, bolos, t-shirts, tote bags, mouse pads, pillows, all sorts of things with the Twist logo emblazoned all over, so that when you're out shopping for your groceries, you can have a lovely kiwi from one of Blair's Animal Corner calendars and the Twist logo to share with people. And they'll say, "What bag is this that you're putting your milk and eggs in?" And you'll say, "It's my Twist bag." And they'll ask you about Twist, and you'll send them to twist.org, and they will be one of our family soon as well. That's right. It's all part of our bigger plan. Also, purchases from the Zazzle store do help support the show and the things that we do. In addition to the Zazzle link, you can also, from twist.org, access our Patreon page. Patreon.com is a crowdfunding community where you can click on the Become a Member button and support TWIS at a chosen dollar amount per month. Once a month, you'll be charged for the level of your support. And each level comes with with little benefits. Anything over $10 a month, and I will read your name in thanks at the end of the show. $10 a month, photon support. It's nice and easy, a great round number. And you'll know that for just about the price of a cup of coffee a week, you will be helping to continue to allow TWIS to bring you science week after week after week. And so I thank you very much for listening to TWIS. I thank you for your support. We really couldn't do this without you.
Can't explain things you've heard more than intuition. A lot of reason shows the way to go. New conclusion. The methods of hypothesis and patience are the only things I need. Put on a pair of goggles and go looking for the things I.
And we're back. You're listening to This Week in Science.
Yes, you are. Hey, Blair, do you know what time it is right now?
Is it that time?
It is time for This Week in What Has Science Done For Me Lately? Our writer this week writes in and says, "Hi, Dr. Kiki, Justin, and last but not least, Blair. As always, I enjoy every week with you. My reason for writing again is scary, but mostly happy. A few weeks ago, my fiance had a medical emergency. We were at home and she had gone unconscious and had stopped breathing.
Oh my gosh.
I heard something odd before she had collapsed. I called 911 immediately on my cell phone. Cell phone technology meant I could stay with her and talk to the operator at the same time. Even with first aid training, it helped to have the extra medical help provided by many years of medical science talking me through it. Thanks, science! EMTs showed up. Still would not have been as quick a response without science. She woke up and got taken to the hospital to have many tests, which got us a diagnosis. While it was not the greatest of news, there are many treatments thanks to science. All I can say is science saved her life,
Wow.
literally. Thank you for continuing to do the great work you all do. Good science to you, Ben Bignell."
Thank you, Ben. Wow. What a scary
Science,
situation.
there's two sides to this, right? One is just finding out more about the universe that we live in, and the other side is
It's a
using
real
science
world.
to make life better.
It's a real world application. right
Yeah.
there.
To help us, and so
Yeah.
many of us get helped on a regular basis. Yeah.
Absolutely. Hey,
Oh my
I feel like
goodness.
3 days a week at least, I am so thrilled about the medical technology of painkillers when I get headaches. I can't even imagine what life was like before you could pop a couple pills and make pain go numb.
Oh.
Exactly. Yeah. And Ben, we are so glad that your fiance is okay. And I hope that she was able to hear this when you're listening to it. Thank you so much for writing in. Everyone out there, remember, you can write in. Please write in. We want you to. We want to read
You
what you
have
have
to
to
write
say.
in.
You
No
must.
choice.
No. I don't know how the forcing is happening. I don't know anything about
Yeah.
that. No. But we would love to know what science has done for you lately. Let us know. Leave us a message on our Facebook page, facebook.com/thisweekinscience, or send me an email at Kirsten, Kirsten, at thisweekinscience.com. We're going to keep filling this segment of the show with stories from you. I realized that after Earth Day, that we started doing the What Has Science Done for You Lately segment 2 years ago on Earth Day.
Has it really been this long? Wow.
We passed our 2-year
I feel like
What
it's a
Has
new
Science Done
segment.
for You
This is how long
anniversary.
we've been doing the show.
It's
New
just so
segments are 2
great.
years old.
New
Yeah.
segment. I know. It's a 2-year-old new segment. Oh my goodness. All right, let's move on to some moony science. Time for some moony science. That's right.
Moony.
Moony, get your moon on. Moonquakes. That's right. The moon likes to shake, rattle, and roll. Sometimes the quakes come from deep within the moon. Other times they are closer to the surface. And apparently, a seismometer deployed by the Apollo missions discovered that there were lots of moonquakes, and they measured a whole bunch of them between from about 1969 to 1977. This was in NASA's passive seismic experiment. So they installed these seismometers at the Apollo landing sites. However, there's not enough data to really figure out where the moonquakes were really originating. And so now we have data from the Lunar Reconnaissance Orbiter, which has actually given us evidence of thousands of potential fault line earthquake
Fault line.
sources.
I didn't think first.
Fault
This is
lines.
This is newsy news to me because did not realize that there was any sort of plate tectonics taking place on the moon.
There are none.
Oh, there are none.
There's
So is the center of the
Interesting.
moon molten?
No,
yes.
no.
Yes. So they think that the center of the moon might still be rather hot. Maybe not molten still, but
Okay.
rather hot.
So what is there to move?
So
Yeah.
the surface of our Earth, we've got multiple plates, and they run into each other, and they slip underneath each other, and they roll on over each other, and they do their dance around the surface of the planet. The moon just has one plate. It's just the crust of the moon. And at one point in time, the moon was very molten, because if it were ejected from an impact of some planetoid body with the Earth a long time ago, that would have been a very hot event, and lots of bits and blobs of planetary stuff glommed together in heat-producing collisions. Hot little moon. There you go.
Okay.
That hot little moon has been cooling
Oh.
millions of years. And
Oh.
what happens when things cool down?
This is compact a bit.
Yes, the
Compaction.
moon is compressing. It's compacting, and so these fault lines are like
Oh,
wrinkles.
They're what are those?
They're just
Shrinkage.
Not trans.
We're talking about a shrinkage.
What are the different plate? Oh no.
We're talking about shrinkage.
Middle school science. I'm losing it.
These are thrust faults, but they're
Oh, thrust
places
faults.
where the surface is contracting, and because the surface is contracting, it's getting shoved up, and things are getting thrust up.
Thrust.
And Yeah, and so now we know that there were a serious number of earthquakes over the years that were measured by the Apollo missions, and now with the evidence of these fault lines, we may be able to better determine the location of future moon missions, of a possible lunar base, because we wouldn't want to put a base anywhere close to one
No,
of these
not a good idea.
scarps.
Put it on
Yeah.
a fault line. No.
Yeah, so
No.
now we know there is oh, and one of the other interesting aspects of this is the quakes seem to happen more often when the moon is at apogee. So its furthest extent in its orbit away from the Earth. And so all where it's a point where all of the gravitational force of the Earth is really directed at the moon and the Earth are pulling at each other before the moon starts the other half of its return orbit around. And so the the cooling of the moon and these gravitational forces of the Earth are what are causing this seismic activity. Pretty
Interesting.
cool. Yeah. So a moon with one plate and no known volcanic or molten activity at this point in time, it still has earthquakes. I mean,
Still,
not earthquakes,
well, they're not
moonquakes.
earthquake, they'd be moonquakes, yeah.
Moonquakes, yes. Still happening. Um, additionally, other moon news, China, we know, landed a lunar rover on the dark side of the moon. It's not
Mm.
really dark, it just is far.
Just
It's
on the other
on the
side.
other side, we don't see it. Um, so on the far side of the moon, this Chang'e 4 spacecraft landed the Yutu-2 rover, and according to their observations of the surface, they have been looking at this basin. It's called the South Pole Aitken Basin, and it's the moon's largest impact basin. And they landed there on purpose because they wanted to get as close to the mantle as possible, or at least get into an impact crater that
Mm.
could have gotten far enough through the crust that it would have brought some mantle back up with it. Because we're trying to figure out, how the moon has been cooling, what processes have been taking place in its formation, and what it's really made of.
Yeah,
And
and
so
because it's all thrust and I guess there's no rift valleys on the moon.
right, right, nothing
What better
bringing
than
that
place
stuff
than a
up.
crater? Sort of like if you wanted to look over geological time, you would maybe go to the Grand Canyon because you could go down to depths and see layers over time, perhaps.
Yeah. And so they're looking at the spectra. This lander has an instrument that allows it to look at the spectra of light reflected off the soil. And it's using its visible and near infrared spectrometer. And looking at the soil in this basin, it does seem as though they are looking at stuff that's not normal crustal material. They don't know for sure, however, because there can be other explanations for the spectra that they did see, but for as far as not having actual mantle samples or these rock samples in hand, this is a promising place for future missions to actually go for rock return, to actually go grab a rock and bring it back to Earth, or even just look at it on the surface of the moon to determine
There's some there's
the
something fun about
process.
it about saying like we have really interesting data. We have no idea what it means.
That's my life. That's most of Antarctic science.
Yeah, yeah, it's really interesting. Can't put it in place with anything else, and we can't really look at it any closer than we have. Yeah.
Exactly. It's the process of going someplace, especially going someplace that's so far away and so far removed from all the nice, easy machines and analysis and easy ways of doing things.
You have to pack everything ahead of time, right? You've got one chance.
Yeah. Yeah, it's amazing. Would you would you ever have thought of volcanism as opposed to glaciology? It's ananother interesting
There
geologic
is volcanism in Antarctica. I can have them all.
You
Oh,
could have
nice.
That's right.
Both. No settling. I like it.
Yes, and so the moon, very interesting. We may head candidate mantle materials at one point in this Aitken Basin. It's a very positive probability. Now, my last story for this section of the stories has to do not with moons, but with whales. Let's
Oh.
bring it right back down to earth. Um, I love this story because we've talked about large organisms and the fact that they are less likely to get cancer on the show. We've talked about this before. Elephants have increased numbers of the P53 gene, which is a tumor suppressor gene. They have lots and lots of copies of this gene, and this is one of the genes in human cancer cases that is often mutated or has problems with it. And when there are the problems, the tumors don't get suppressed, and and cancer spreads. However, elephants, they've got a bunch of copies, and they suppress tumors, and they don't get cancer. Large animals, large people have a higher probability of getting cancer just because they have more cells and thus more cell divisions. And every time a cell divides, that increases
Potential.
the probability of a mutation of something that could cause cancer. And so the idea is that large organisms, elephants, whales, other big things, should get cancer more often
Higher
than they
rates.
at higher rates, and they don't.
Mm.
And so we wanna know why, because if we can figure out why these other organisms don't get cancer,
We could
maybe
stop cancering ourselves. Yeah.
ta-da! Yes, and so, researchers at Arizona State University at the Arizona Cancer Evolution Center, uh, have been looking at the genome of a humpback whale named Salt.
Hmm.
They got the DNA from salt. Salt is well known to researchers and whale watchers and is cataloged by the Center for Coastal Studies, has been around since the 1970s. She's really well documented and a pretty old whale. So you would imagine if there was cancer going on or anything, there would be stuff to see in her genome. However, so they looked at Salt's genome and they got about 2 billion short sequences from a DNA sequencer. They put it back together through genome assembly, and they have about 2.7 billion base pairs. This is not quite as big as the human genome. They also sequenced RNA, which is important for the control of the genome, figuring out what gets expressed and what does not. And then they compared the humpback whale genome to genomes of other mammals, blue whale, fin whale, bowhead whale, sperm whale, some dolphins, other mammals, and they looked to see what was going on in the genome. And they found that there's some parts of the whale genome that have evolved faster than in other mammals. But overall, whales have undergone slower evolution than other mammals. So it's a very interesting like dichotomy in the speed of adaptation in certain sections of the genome. And they found that the genome, these parts of the genome, they contain genes that control the cell cycle, which is how the cell grows and divides, cell proliferation, making new cells, DNA repair, very important for controlling those mutations. And this is all part of just normal cell function. And these are the areas that have had sped up uh, evolution, adaptation. A lot of the genes that they found have similar analogs in human genes. In human cancers, a lot of these genes are mutated. And so, additionally, the whale genome has duplications in tumor suppressor genes as well.
Hmm.
So, there's a lot of interesting, unique stuff that's not the same as what happened in the whale genome. where not whale, in the elephant genome, where in the elephant genome it was just the p53 tumor suppressor duplicating, duplicating, duplicating. And here there's just a lot of stuff controlling cell cycle and making sure the cell cycle works. They accumulate fewer DNA mutations over time, and that might have something to do with it as well.
So this just sounds like really big animals have had a case of convergent evolution with cancer suppression. That's what this sounds like. Just like the quills on a porcupine versus a hedgehog are completely different, but they serve similar purposes, and they do not have a common ancestor that had quills.
Why?
It's something that works.
But it's also that we're only seeing the positive result of this control, right? So we're only seeing really large animals that have good cancer suppression. What we aren't seeing is those animals that were more than happy to get large and were heading that way, but didn't have cancer suppression. And so the larger they got, the more it affected the life cycle. So we're also seeing the result of having the benefit of having good cancer suppression and allowing life forms to become larger. What we're not seeing is all of those that could not pass that threshold.
That didn't make it.
Yeah.
Right.
Well, I mean, and that's the definitely part of the main tenets of how convergent evolution works is that there's a selective pressure, and random mutation has responded to that selective pressure in different ways to similar results. So
and it sounds like what you were describing was also of increased ability of demethylation to prevent mutation from taking place. So that's also that's also an interesting aspect of this is like we're going to prevent the things that could lead to increased.
Right. So now we need to take cancer-prone laboratory mice and mess with their genome and see what happens.
Right. I mean, the thing here is
the answer to everything. Yeah.
What we're seeing here is that long-lived large animals, which undergo many, many cell division cycles, have evolved successful cancer suppression programming. And so it means that it is not something that is incompatible with long life and large size. So could these adaptations be something that could be added to the human genome? Is it something that we could use to target treatments, specialized treatments for various cancers? So let's CRISPR up some lab mice. Let's start figuring it out.
There you go.
There you go. Justin, what do you have?
I've got some stories. This is Neanderthals and modern humans diverged around somewhere in the 300 to 500,000 year ago range from a common ancestor that we shared. And we know this mostly based on the finds that we have found and ancient DNA analyses attempting to sort of trace back traits and rate of genetic evolution. However, in a cave site in the mountains of Spain, a challenge to this interpretation of the timeline has emerged. This is Cima de los Huesos, a cave site where archaeologists have recovered fossils of about 30 Neanderthals. And previous studies have dated this site to around 430,000 years ago, making it both one of the oldest and largest collections of Neanderthal remains discovered. What's interesting here is that this is very close to the divergence point, and it's all the way in Spain, which is by itself interesting. But beyond this, what they're looking at is the teeth of these Neanderthals. They've analyzed dental evolutionary rates among hominins, and they find that no matter where you look, the rate that it takes teeth to evolve is pretty along the same curve. It takes about the same amount of time, whether you're getting bigger teeth or recessing down to smaller teeth. Time frames are consistent across hominins over time. And if you look at these Neanderthals, and if you look at the teeth of these Neanderthals, and there's some possibility so that that these Neanderthals are actually very likely the ancestors of all the Neanderthals that we know of after. They're sort of in line. They're not an offshoot that was isolated and unrelated, both genetically and morphologically. But if you look at their teeth and start to trace it back, the time frame is 400,000 years earlier to a common ancestor, putting the divergence somewhere in the 800,000 year ago category, which is really interesting for a few reasons. One of which is that 800,000 year ago common ancestor eliminates a lot of the candidates that we would have pointed to previously and said, okay, this range of hominins that was living here or there, that could be the common ancestor. It pushes it back beyond a known common ancestor to something much more primitive in the context of early hominins. And also sort of suggests that there might have been more convergent evolution between these disparate groups, that they both sort of evolved in cognitive ability over time in similar ways. This is Dr. Ada Gomez Robles, UCL Anthropology. She says, any divergence time between Neanderthals and modern humans younger than 800,000 years ago would have entailed an unexpectedly fast dental evolution in the early Neanderthals from Cima de los Huesos. There are different factors that could potentially explain these results, including strong selection to change of teeth of these hominins or their isolation from other Neanderthals found in mainland Europe. However, the simplest explanation, which is usually the one that is preferred, is that the divergence between Neanderthals and modern humans was older than 800,000 years. This would make the evolutionary rates of the early Neanderthals from Cima de los Huesos roughly comparable to those found in other species. And so you would have to consider Cima fossils as likely ancestors of later Neanderthals based both on the anatomical morphological features and DNA analysis. Yeah. So it looks like everything that we know about the Neanderthal evolutionary path is being challenged by
by teeth.
Being challenged.
Right.
A nice way of saying it was wrong.
Well,
we don't know. We don't know that. I know.
So this is okay. This is of course. I'm going to do the blanket statement. This is how science works.
Yeah.
You're right with all of your data points because they're good data points until there's a data point that says your data points aren't the whole story. And it doesn't make them wrong. It just means that the story is getting added to, that there's more to the story than you knew because you didn't have the data points. And speaking of data points, there's more data points. Oldest human DNA from Scandinavia has been sequenced from maybe the least likely of places. Bits of chewed birch bark pitch spit out like wads of already been chewed gum.
What is birch bark pitch?
So this was gum.
Sap.
This was like
It's like
pitch,
it's like sap from a tree.
That was chewed. It was and actually up until like this is a 10,000-year-old sample that they found. But this was you could find this behavior of chewing this birch pitch up until very recent times, like within the last hundreds of years, like this 1,000 years. This was gum in Scandinavia, and it was passed down from 12-year-old to 12-year-old. I'm assuming somewhere at that age, people picked it up. So this is according to Stockholm University, which has published their findings in communications biology. Few bones of this time frame have been found, and few are still preserved enough for DNA to get the genetic analysis. The DNA derived, though, from the spat out gum wads, pitch wads, from 3 individuals in the around It's cutting up to about 10,000 years ago. The investigated pieces come from Husby Clev, near the Mesolithic hunter-fisher site on the Swedish west coast. The excavation was actually done. The discovery of these wads of chewed pitch was found back in the early 90s, at a time when DNA extraction methods weren't a thing yet for something like this. So they've been sitting. And then, so this is Pierre Pearson and Michael Mann. I'm messing up the names. It's fine. Proposed to look further at hunter-gatherer DNA in these chewing gums from Husby Clef. They were hesitant, but really impressed that archaeologists took care during the excavations back in the 90s to preserve the fragile material, says Natalia Kusheb, who is affiliated with Museum of Cultural History in Oslo and performed some of the experiments and is now a promising PhD student at Uppsala University. It took some work before the results overwhelmed us, as we understood that we have stumbled into this almost forensic search, sequencing DNA from these mastic lumps which were spit out at the site some 10,000 years ago. Results show that genetically, the individuals whose DNA was found show close genetic affinity to other hunter-gatherers in Sweden in that time frame and the Ice Age Europe. However, what's sort of interesting is the tools that they had. The tools that were being produced at the site that were found were not classic Scandinavian.
Mhm.
They were from the East European plain, which is now Russia. And yet, if they also looked at it, they've also found that the genetic relationship was more like a Western Europe.
So they borrowed some tools. They're like, "Hey neighbor, let me borrow some tools."
Yeah, which in our day and age, when plate tectonics aren't a big deal, like for travel, doesn't seem like Eastern Russian plain, Western. It's a flight, it's a train ride, it's whatever. But this is kind of an impressive time frame, 10,000 years ago, for this much sharing of technology amongst peoples over really vast ranges. Something works, everybody picks it. It's like a meme in the ancient world, traveling like vast distances and over quite a bit of time. DNA from these ancient chewing gums have enormous potential, not only for tracing the origin and movement of peoples a long time ago, but also providing insights into their social relations, diseases, and food, says Pierre Pearson, Museum of Cultural History in Oslo. Much of our history is visible in the DNA we carry with us. So we try to look for DNA wherever we believe it can be found. I
can't wait for people to go and archaeologically find the chewing gum wall. The chewing gum wall in near Pike's Place in Seattle. Yes, it's a wall covered in chewing gum from people all over the world who go and stick their gum on the wall.
Or go find the elementary school classroom and check under all of the desks.
Exactly.
So this is also the idea for my reality show, where you go around and you find gum on sidewalks or under tables and diners, and you do analysis. You compare it to a genetic, the genetic thing that the 23andMe or whatever people are doing, and you go track down the person.
You go find them.
You confront them. It's
like you come with a 3D rendering of their
on
face.
a sidewalk.
Yeah.
You throw it back at them.
Oh, that would be funny. Oh my goodness. I'm not going to throw gum at anybody. I hope you don't either. But sometimes animals do.
What?
It's time for Blair's Animal Corner.
Yeah, Blair.
Yeah. Where's the song?
Loves are creatures, great and small. Biped, millipede, no pet at all. You want to hear about animals? She's your girl. Except for giant pandas and squirrels. Then
Got Blair.
I have sexually transmitted infections. No, I have animals.
I'm so sorry to hear that.
Animals with sexually
you got one of the
transmitted
good ones.
infections. Specifically, I am looking at invertebrates with sexually transmitted infections. This is a study from the Australian National University, ANU, and this was looking at how sexually transmitted diseases can act as a mediator for sexual conflict.
What?
I will repeat. How could an STD be good? Well, it depends on what your goal from sex is. So this is when the evolutionary interests of males and females do not mix. For males, usually we think about males, they're just trying to spread their genetic material as far and wide as they can. It's cheap. It comes back later. It's an endless supply. It doesn't really go bad. With an asterisk, we've talked about that on the show before. They're just trying to get their genetics out there as much as they can. For females, obviously, there is a much heavier investment. Eggs are finite. Producing eggs and nurturing eggs can be very energetically taxing. It can be emotionally taxing because of the investment as well. Depending on the species, they have to make investments and decisions for their progeny. The time and effort related to reproduction is way bigger with females than males, generally speaking, specifically with animals that have internal fertilization. So this conflict means that there is this kind of difference of priorities and reasons to mate. And what males want more than anything is to make sure that once they mate with a female, that nobody else's sperm ends up competing with theirs. So they just want to make sure that they have monopolized the eggs that they had access to. So there are different ways that you can do that, like with spiny genitalia, like with mating plugs, cementing up the female opening. These sorts of things can make sure that those eggs are only being fertilized by that male's sperm. It turns out STDs could work in the same way. And that's because when an animal becomes infected with a virus or bacteria of any sort, there's usually two different ways that they may respond. The first is, oh no, I'm sick. I better have a bunch of offspring right now because I'm not going to survive and I have to get my DNA out there as fast as I can. That's called terminal investment. The other response to an infection is I need to invest everything in my body, all of my energy into fighting that infection, getting better, and then I will be able to reproduce later. For animals with really long gestation periods, like most mammals, that is often the way that they go, because if they succumb to illness while pregnant, then their baby also dies. So they want to, a lot of the time, this is why if you get really sick, people have miscarriages, stuff like that, is because the body is focusing energy on getting the host body well again before reproduction. So these are kind of the two different ways that a female body can respond to infection related to reproduction. So when insects have terminal investment, which is often the case because they've put enough energy in, their life is not long, it doesn't take long for them to pop out some fertilized eggs. If they have that approach, then it actually could benefit the male to get the female sick with an STD. So this is because once they are feeling the effects, their body responds to the fact that they're sick, that means they just lay eggs, fertilized eggs, with the male sperm that they've received. They don't have time to mate with anyone else first. They don't hold back eggs. They just lay them all out there. And so this is a potential reason, evolutionarily, for STDs and STIs to exist, which is, it's still kind of in the hypothesization phase at this time. That's not a word, but it's like there is a hypothesis. There is potential evidence to support it, but it has not been turned into a formal experiment. So, yeah. So The other piece of this that is very intriguing is that previous studies have shown that in at least some animal species, males have lower immunity than females. Things like the man flu, right? So it's possible that these males actually have lower immunity so that they will catch the STI to then pass it on to a female. So
Fascinating.
interesting
That's a really
thoughts.
Yeah, very interesting thought. I mean, when we think about these, infectious diseases, you think of it from the perspective of the disease very often, but everything is a system, right? And so it's not just the virus or bacteria or parasite, whatever it happens to be, getting in there and doing what it wants. It has to pass along, it has to survive, and it's doing what it has to do. But then the ones that are infected also want to survive, also want to take advantage somehow of the situation. And so it's a tit for tat, predator prey. There's adaptations that take place to allow, better survivability. And so who knows? I wonder.
I mean, there could be a benefit. So the next step is to actually do a laboratory study with eucalypt beetles. They have a very unusual sexually transmitted mite that lives under their wing case. So it is transferred.
I've just got it.
I
just keep it right under my wing.
The mites are just like jumping from one to the other. But so this is something that will be easily tracked through laboratory conditions, and they can see how many legs the females are laying, who the fathers are, all these sorts of things to kind of see if there is a direct benefit to having and transmitting an STI.
Fascinating. Oh my goodness.
Indeed.
All I'm going to say is that no.
Hey, nature, you don't have to like it.
I know. It doesn't have to like me either. That's right.
Another piece of our very own nature that is deep-seated further back in the evolutionary history than we may realize is test anxiety and lack of performance on tests. So this is a study from Johns Hopkins University, and this is looking at the distinction between knowledge and performance, looking for insight into how environment can affect those two things. So a great example of the difference between learning, knowledge, and performance is the difference between studying for a test, knowing your answers, paying attention in class, and then bombing the test. Why is that? Why, even though we know the stuff, can we not perform properly when we are asked to recall it? So a lot of people just say it's because they don't test well, they have test anxiety, but there might actually be some scientific evidence here that there's something about the environment that is skewing the results of these tests. So this study looked at ferrets, mice, and rats in different reward-based tests. And so in the first one, they took a group of mice, they trained them to lick water through a lick tube. So it's like a little metal tube that sticks out, and there's water, and there's a meniscus at the end. So licking it, they get the water out of the tube. It's just like a liquor that you'd have in a guinea pig enclosure or something like that. And so there would be water present after hearing a tone. They were taught to not lick it after hearing a different unrewarded tone. So that's when the lick tube was empty. It would take mice about 2 weeks to learn this when there was a water reward present. But in the point of early learning, at around 3 to 5 days, they tested their levels, and it was about 50% success, so not any better than chance. But when they removed the tube completely and they just had the primer space, kind of the stage, and then they had the tones played, they would lick at 90% accuracy at no tube at all.
What?
Which means they understood the task. Tone means lick. days before they showed knowledge when there was a reward present. So the reward present to teach them what they needed to know, how else would you teach a mouse to stick out their tongue, was helpful. But when it came back to testing knowledge, having the reward there appeared to be detrimental. The team also, in a second test, had mice press a lever for water when they heard a tone. In another one, prompted rats to look for food in a cup when they heard a tone, but not if there was a light before the tone. They had rats press a lever for sugar when the light was presented before a tone, had rats push a lever for sugar when they heard a certain tone as compared to other tones, and prompted ferrets to differentiate between two different sounds for water. So in all of these experiments, the animals performed better when they didn't have the rewards present.
So this
Rewards are
means that I
bad.
shouldn't give grades on tests.
Maybe, or maybe you shouldn't tell them when they're being tested. Maybe that's what it's about.
Or when they're being graded.
Yes.
Right. Yes.
Yeah.
It's maybe that anticipation of the grade or of the reward.
Right.
We get maybe the animals, not thinking of students, animals maybe focused on the reward more so than the actual test.
Yeah, I think about it like a second guessing machine, kind of. So if the lick tube is there, if the place where the water comes from is right in front of your face, are you going to trust what you learned and not try for water? Or are you going to try for water because there might be water in there?
Mhm.
Well,
And the
Make it
test,
fine.
especially a multiple choice test, if you think you know the answer, but there's an answer that might sound right, your gut told you it was A, but B also sounds right. Maybe I should pick B. Which one is it? Maybe it's all of the above. You know, there's something there that when the pressure's on and there's this dangling fruit potentially, I think there's this impulse to test your options. So I don't know exactly what's happening here, but there's a clear relationship between having a reward present and that affecting performance that does not show intelligence. It does not imply intelligence.
well,
It actually affects it affects what we call intelligence. It affects
Right.
our perception of it.
Right.
maybe I'm also getting something very different from this because
Oh, let's hear.
I'm getting that there's a reward present if you get the right answer. So they have and then they have like a 50-50 chance. Right?
Mhm.
So if the reward is present, look for it. Just try.
Oh,
Guess.
absolutely.
That's
Yeah.
what
Guess
Blair was
away.
saying,
Guess away.
right?
Yeah.
Yeah.
Guess away.
Yeah.
And then now there's no reward present. So it's as if you think you're getting it wrong because you're not getting rewarded. So you're trying harder now to get a reward because you didn't get rewarded. Oh, maybe I got it wrong. I got to concentrate. Okay, try again. Didn't get a reward. Okay, this time I'm going to get it right. I'm going to really focus. Okay, that's the tone. There was a light. I'm not going to do it. Now there's another tone. That's the right tone. Now I'm going to try again. I didn't get it. Okay, this time I'm going to get it right because I'm going to get the. It seems like it's an escalation of denying a confirmation of the right answer or the reward. That's creating a greater emphasis on trying to get it. Versus the other one where it's like, I got it right. Oh, this time I missed. Whatever. This is gonna be another question. I'll get the reward.
Interesting. Yeah, I think that's an interesting way to look at it. The way I was thinking about this was when you're training dogs, but also when you train other animals as well. When you're starting to teach them a behavior, you give the reward every single time the second they do it right. And as it becomes more and more easy for them, you can have instances where you ask for a behavior and they give it and you do not give them a reward. So for example, if you have an 8-year-old dog that's known how to come when called for 7 of those 8 years of their lives, by the end, you're not giving them a treat every single time you say come and they come to you.
Yeah. And I would again say that's because maybe I didn't get there quick enough. I'll try harder next time.
Yeah.
I'll focus.
Just
possible.
try harder.
Yeah. But so the implications of this study obviously are pretty vast. The one that I first thought about was, oh no, have we been shown yet another way that the scientific community has not been testing on rodents properly? Because we've talked about how it turns out they need higher temperatures than we've been giving them. And it turns out that they need more living spaces so they can separate their latrine from their bed. And then also now, have we been reinforcing and training them wrong? So have we misread their intelligence, and are we not testing exactly right?
And there's this really bizarre socioeconomic aspect of this, which is not in the study, but is totally reflected. If you are, it's like the marshmallow test. If you're confident that you can get a reward later, if you can, if you are comfortable with the amount of rewards you've gotten, it allows for more risk taking. You can take a risk of saying, well, I don't know if this is the right answer. I'm going to try.
Interesting.
I'm going to guess.
Yeah.
Whereas if there's limited resources and it becomes very important to get it correct, you're going to only try those things that are going to work. Which in the marshmallow test means if the strategy is you live in a world of limited resources, the actual best strategy is to take the marshmallow right away because you have less opportunity later. In this scenario, it also seems like that might be something.
So maybe we need to, next step for this study would be to kind of look at the frequency of how often you need to give a reward to still get good behaviors and things like that. But the other implications that the authors of the study propose, which I just want to throw out there, is that ultimately they're looking at how performance is affected by these variables. And so for one, obviously, this could be used to improve testing environments for children, as was brought up. But the other thing, which totally blew my mind, was that this could potentially help with Alzheimer's, because it could help maintain lucidity for longer periods of time if we can figure out how to promote the right performance, the right pathways in the brain. Are those not being used sooner because there are other things in the environment happening? So they took this way outside of the box here, but I think it's very interesting. It's a question of how our brain works. So
turns out negative
respond to and how we
reinforcement is good for
behave.
education.
Who knew?
That's not what I'm hearing. I don't know.
I don't know. What are you hearing out there?
Yeah.
Everyone out there, let us know what you are hearing in this study. It is time for us to get to our quick stories at the end of the show. We got 10 minutes, everyone. Let's get it done. All right. I have a couple of quick stories. One of Blair's favorites is artificial intelligence, and how artificial intelligence is getting smarter and smarter. Well, researchers trained a computer model of virtual brain cells, an artificial neural network, to learn how to identify numbers of objects in images. The network developed neurons that responded to specific quantities, and these artificial neurons are very similar to number sense that we have in humans, being able to have an idea of how many numbers, how many objects are in a group of objects. And the behavior of these neurons very closely matched the behavior of neurons in monkey brains that were tested. And so there are very specific neurons in our brains, in monkey brains and other mammalian brains, for number sense, these number sensitive neurons. And it turns out AI neural networks can develop them too. Now they can count.
No.
They'll count better than you. And while we're counting, let's count on those photosynthetic bacteria that exist in our oceans. As we talk about plastics in our environment, we have often commented on this show about the lack of research that supports the claim that plastic is bad for the environment, bad for life in the environment. Well, a new study out in communications biology has looked at a bacterial species, Prochlorococcus. And Prochlorococcus, it produces about 10% of the oxygen that we breathe. And they found that leachates, which is basically they put plastic in seawater and then the plastic chemicals came out in the water. And so they put that water on the bacteria. And lo and behold, bacteria's growth rates went down and oxygen production went down. Genes related to oxygen production and photosynthesis and carbon cycling and all that kind of stuff in the bacteria, down regulated. So we have a nice little study that suggests that yes, indeed, plastic that ends up in our oceans could potentially affect the bacteria that produce the air we breathe.
Yeah,
Wow.
the ocean. It's kind of important.
Kind of important, everybody. Let's get on that plastic cleanup thing, okay?
But don't just clean it up by pulling it out, because then you disturb the nostrum, which is
Yeah, right. We'll do it better. Justin, tell me a story. Faster.
Speed kills is a phrase that is often used in reference to responsible or irresponsible automobile operation, also irresponsible or just unregulated narcotic usage.
Mhm.
But for people who don't happen to be doing one or both of these at the moment, speed might actually be a good thing. People who report that they have a slower walking pace have a lower life expectancy than faster walkers. According to a new study conducted by researchers, National Institute of Health Research, partnership between Leicester Hospitals and University of Leicester and Loughborough University. Research using data from UK Biobank. It's a pretty good meta sample. 474,919 people recruited within the UK found those with habitually fast walking pace have a long life expectancy across all levels of weight status, from underweight to morbidly obese.
That was one of my questions.
Yeah, so this is kind of fascinating. Underweight individuals with slow walking pace had the lowest life expectancy.
Huh.
So it is untethered from weight here dramatically. And in fact, inversely in a way, because the slower individuals with the larger weight outlived the slow walkers with the low weight.
Get your power walk on. Get
Yeah,
it.
I wonder if it's related to cardiac health, though.
Mm-hmm.
That's the thing. It's about 8 years difference. So those who are underweight and slow walking had an average of 64-year lifespans versus 72 years for women. So women lived longer even if they were skinny and slow walking.
Power walker.
This is Professor Tom Yates, who is a professor of physical activity, sedentary behavior, and health at the University of Leicester. He was the lead author of the study. Our findings could help clarify the relative importance of physical fitness compared to body weight on life expectancy of individuals. In other words, the findings suggest that perhaps physical fitness is a better indicator of life expectancy than the BMI body mass index, and that encouraging the population to engage in brisk walking might add years to their lives. So
Makes sense.
Yeah. So
people have been talking about BMI for years as it's not so great. Got to figure out something better.
It's always been very problematic. But so the interesting thing about this study is they're self-reporting over like 500,000 individuals, whether they're fast walkers or slow walkers. But it's not that if you are a slow walker, it's not that you can't change things. You can walk faster. This is the thing. It's not like, according to the genetics of 500,000 people, life expectancy is based on. No, you can actually pick up the pace, regardless of where you are in BMI or any of this nonsense. If you walk fast, you will live longer. So keep that in your mind, and you'll save time. And by saving time, you'll have more time on the planet. Of those years, it's like living.
And it's now time for Blair's story. Blair, what's your last story?
Oh, I have some catapulting spiders.
Okay.
So it's the triangle weaver spider, or Hyptiotes cavatus. They actually rear back. They use their web to store elastic energy they release their grip and catapult themselves at a furious speed towards unsuspecting prey. So this is from University of Akron in Ohio. In Ohio, people have written about these observations but have not looked at them in lab conditions. Now, under lab conditions, we have seen high-speed videos, and they have reported that they spring forward at the equivalent of around 400 body lengths per second. So that's around 772 meters per second squared. So that is very fast. This is something that we're seeing for the first time, but now it's possible other animals might be doing that. And the other really weird question mark is we don't know how the spiders are holding their catch mechanism, how they're holding onto the web as they launch forward, which is very interesting.
Catapulting spiders.
Spiders.
Where do these things live so I can not move there?
So it sounds like Ohio.
Ohio. All right. Ohio. Okay, I'm not moving to Ohio. I know there are lots of nice people in Ohio.
There's a couple.
Enjoy Ohio.
Yeah.
Catapulting spiders.
Catapulting spiders. I'm just assuming it's like jumping spiders. They're probably really cute. Because when someone said jumping spiders, I was like, no. And then I saw pictures of jumping spiders, and now I love them. So maybe catapulting spiders are adorable. Who knows?
We'll have to learn to love them. We have come to the end of another episode of This Week in Science. It's another episode. Done. Thank you all for joining us once again to talk about all the science. I would love to say thank you to Fada for introducing us to Dr. Hulbe, for bringing us this interview this evening. Dr. Hulbe, thank you for joining us tonight.
Oh, it's been so much fun. I'm a fan, and I'm like, I have front row seats.
Yay! I'm so glad that you stayed through the show as well. Also, thanks to Identity4 for recording the program so that we can have a podcast, and to Gord McLeod for helping to keep our chat room a nice and happy, wonderful place. Thank you for maintaining that. I would also like to take this moment to thank our Patreon sponsors. I would like to say thank you to... I have things lined up here. Thank you to Paul Disney, Richard Onemus, Ed Dyer, Andy Groh, Stu Pollock, Philip Shane, Ken Hayes, Harrison Prather, Charlene Henry, Joshua Fury, Steve DeBell, Alex Wilson, Tony Steele, Craig Landon, Mark Mazzaros, Jack, Matthew Litwin, Jason Roberts, Bill K, Bob Calder, Time Jumper 319, Eric Knapp, Richard, Brian Condren, Dave Neighbor, Corinne Benton, Adam LaJoy, Sarah Chavez, Rodney, Tiffany Boyd, John Bertram, Mountain Sloth, Seth O'Gradney, Stephen Alberon, John Ratnaswamy, Days Friedel, Gerald Myshak, Andrew Swanson, Paul Ronovich, Sue Doster, Dave Wilkinson, Ben Bignell, Richard Porter, Noodles, Kevin Reardon, Christoph Zucknerek, Ashish Pants, Ulysses Adkins, Artyom, Rick Ramus, Paul, John McKee, Jason Olds, Brian Carrington, Christopher Dreyer, Lisa Suzuki, Jim Drapeau, Greg Riley, Sean Lamb, Ben Rothig, Steve Leisman, Kurt Larson, Rudy Garcia, Marjorie, Gary S., Robert, Greg Briggs, Brendan Minish, Christopher Rappin, Flying Out, Aaron Luthen, Matt Sutter, Mark Hessenflow, Kevin Parajan, Byron Lee, and E.O. Thank you for all of your support on Patreon. And for those of you who are interested in supporting us on Patreon, you can find information at TWIS.org. Also, on next week's show, we will be broadcasting live once again online at 8 p.m. Pacific time at twis.org/live. You can find our chat room there too. But if you can't catch us live, don't worry about it. We are a podcast and we're on YouTube. So you can find past episodes again at twis.org or on our YouTube channel.
Thank you for enjoying the show. TWIS is also available as a podcast. Just Google This Week in Science in your iTunes directory, or simply This Week in Science in anything Apple Marketplacey.
For more information on anything you've heard here today, show notes will be available on our website. That's at www.twis.org, where you can also make comments and start conversations with the hosts and other listeners.
Or you can contact us directly. Email Kirsten at thisweekinscience.com, Justin at twistminion@gmail.com, or Blair at blairbaz@twis.org. Just be sure to put TWIS, TWIS, somewhere in your subject line. Otherwise, your email will very likely be spam filtered into oblivion. You can also hit us up on the Twitter, where we are at TWIS Science, at Dr. Kiki, at Jacksonfly, and at Blair's Menagerie. We love your feedback. If there is a topic you'd like us to cover or address, a suggestion for an interview, a haiku that comes to you tonight, please let us know.
We'll be back here next week, and we hope you'll join us again for more great science news.
And if you've learned anything from the show, remember,
It's all in your head.
This week in science. This week in science. This week in science. This week in science, it's the end of the world. So I'm setting up shop, got my banner unfurled. It says the scientist is in, I'm gonna sell my advice. Show them how to stop the robots with a simple device. I'll reverse global warming with a wave of my hand. And all it'll cost you is a couple of grand. This week's science is coming your way. So everybody listen to what I say. I use the scientific method for all that it's worth. And I'll broadcast my opinion all over the earth. Cause it's This Week in Science. This Week in Science. This Week in Science. 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 This Week in Science. This Week in Science. 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 I've got one disclaimer, and it shouldn't be news, that what I say may not represent your views, but I've done the calculations and I've got a plan. If you listen to the science, you may just yet understand that we're not trying to threaten your philosophy. We're just trying to save the world from jeopardy. And This Week in Science is coming your way. So everybody listen to everything we say. And if you use our method instead of rolling a die, we may rid the world of toxoplasma. Got the cause it's This Week in Science. This Week in Science. This Week in Science. 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 This Week in Science. This Week in Science. 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 I've got a laundry list of items I want to address, from stopping global hunger to dredging Loch Ness. I'm trying to promote more rational thought, and I'll try to answer any question you've got. But how can I ever see the changes I seek when I can only set up shop 1 hour a week? This Week in Science is coming your way. You better just listen to what we say, and if you learned anything from the words that we said, then please just remember it's all in your head. Cause it's This Week in Science. This Week in Science. This Week in Science. 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 This Week in Science. This Week in Science. 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 This Week in 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 Science.
And we come to the end of a show once again. It's the end, it's the end, it's the end. Ta-da. The end of every show. We did a show. Hey, everybody, I forgot to announce it on the show. Santa Fe, June 15th. We'll be podcasting in Santa Fe at the Interplanetary Festival. For all you Santa Fe people. Hey, Fada, I'll get the story in there. I don't know where it is right now. I'll find it. I did find it. Thank you for reminding me. It will go there at some point. I will do it. Where What's up, Blair? You have no microphone. Your microphone is muted.
Sorry.
Oh, there you are.
My bad. I am working on the newsletter.
Oh, cool. Yay. You had asked about interviews. The next interview that I have specifically scheduled is June 5th.
Okay.
It is with Matthew Stanley, and he's written a book on Einstein and his theory of relativity and World War I, and how World War I made getting his theory of relativity out to the world very difficult. Mm-hmm.
Okay. Well, let me.
And so we're going to be talking about the state of science in the early 1900s and how nationalism and war affected it. And Einstein, because Einstein.
Einstein.
Oh, we lost a Dr. Hulbe. She was great. Very nice. Very nice. How nice that she hung out for the show. Front row seat.
Okay, say it again.
fun.
On June 5th, we will be speaking with
Matthew Stanley. Let me find you a link to his book. And oh, that didn't work. Hey, Kiki, let's actually type in the right place. Matthew Stanley. And yeah, he is a professor at NYU.
So is he a doctor?
He is a doctor. He has a PhD in the history of science.
Ooh. Ah,
Yeah.
I've heard of this.
Mm-hmm.
Professor at NYU?
NYU.
I'm guessing that stands for not your
New
university.
Not your university.
Not
I'm just
yours.
guessing. I have no idea.
Yeah.
I have to go due to
Where are you going?
prolonged states of sleep deprivation.
Oh, why are you so
I-
sleep deprived?
I've been getting less than my quota.
Why?
There's
Why?
no why behind it. It's just, sometimes you sleep a lot, sometimes you sleep less. But I will be back here next week, a few hours before this
Okay.
point in time. And
Oh,
I will see
here's
you all
his
again.
here's his book. Here, I'll give you a Kirkus Reviews link.
I don't want to know the book. I don't want to hear this. I can't stand pre-searching.
This is for the newsletter, Justin.
Oh,
Here, I'm putting it in I just put it in the chat room.
Oh, great.
I think it'll be interesting. Hey, everyone in the chat room, if you're interested in history and science and war and Einstein.
Oh, yeah.
It's going to be fun.
You had me the last minute, you had me again.
It's going to be great. It's going to be good. The name of the book is How Relativity Triumphed Amid the Vicious Nationalism of World War I. Einstein's War.
No, it's not his war.
Called Einstein's War.
That's not how you should say it. Okay. Good night, everybody.
Good night. I hope you actually get some sleep.
Oh, yes. This is
yes.
If it hasn't if it's not already happening and I'm not talking in my sleep right now, I don't know what's taking place.
Get some sleep. Go to sleep. Go to sleep. Justin, sleep.
Okay.
We'll start singing lullabies. Go to sleep. Strange theremin sounding lullabies.
Okay, I have a couple things I need to talk to you about.
Awesome. Let's do it.
Okay, so first thing, I'm getting interviewed on a podcast coming up.
Yay! Where?
Mostly about my work with Noki and
Uh-huh.
optimism in conservation education related to climate change. And it is going to be Citizens Climate Radio.
Woohoo!
And it's so funny. He was emailing with the Noki project manager at the New England Aquarium, and she looped me in after they started the conversation a little bit, and then she introduced me, and I mentioned our podcast, and apparently he's a listener.
Oh, how fun.
Which is very fun. But so that's coming up pretty soon.
Great.
So I think I might be doing it next week actually, or the week after. I'm not sure.
Awesome.
But I wanted to know if there was anything in particular that you wanted me to plug on that, other than just telling people to go to our website, subscribe, all
Mm-hmm.
that good stuff. Okay.
Yeah. No. Just TWIS.org and
Great.
get people, if people are interested in your fun animal science and more climate, environment, and other science stories,
Mhm.
that
Okay.
we do our weekly podcast where they can find that.
Great.
Yeah, I think that would be great. Super helpful.
Cool. Okay. The other thing, I wanted to look at, oh man, I like MailChimp a lot, but there's some stuff you can't do, which is kind of frustrating. Is about the newsletter. So, right now, what we have in it is just welcome to the newsletter, and I changed it from saying it was going to be weekly to monthly.
There we go.
Realistic.
Mhm.
And then we have just blurbs from our bios from the website, some information about TWIS merch, some information to email you if they want to be added to the newsletter, so people can forward this to people and then they can read it and decide if they want to be added. And then I'm going to have information about the latest episode that was published to YouTube and then upcoming stuff. Is that enough for this one? Do you want more in there?
Is there anything else that we'd wanted to have in there? I don't know.
Okay. Well, think about it.
Yeah, I'll think about it.
Obviously
I mean,
not going to do anything right now.
it's a lot, but
Yeah.
at the same time, if we're going to do it only monthly, we also want to have something that's like not just
Right.
what people are getting from the podcast. So
Yeah. So I wasn't sure
Yeah.
if for the very first issue, if you wanted to just be like, here's TWIS, or if you wanted to have more.
Didn't you send out the hippo one?
I sent out the hippo one.
Yeah.
That was like a special thing that
Yeah.
didn't have any, it didn't have much that was actually TWIS specific in it. It really had just a
Right.
bunch of hippo musings.
That's fine though.
Okay.
That's fine. Yeah, I liked your hippo musings, and yeah, no, I mean that's kind of the fun thing is like we can do, you know, if Justin actually writes something for it, then we
Yeah.
can have a rant from Justin or whatever it is.
Great.
Um,
Okay.
yeah.
Yeah,
or
because
can-
I don't want it to
can
be
write
too
something.
long, but I also don't, yeah, I do want it to have some sort of added value. So
Mhm.
you can look at so I made the initial one I was working on, I turned it into a template, and then this one is called issue number 1.
Okay.
And then if you want to look at it and let me know if there's anything else you want to add, since we have over 200 people on the mailing list, I think it would be cool to get something out pretty soon. So I'm just
Yeah.
gonna like I said, I'm gonna throw in a link to last week's episode on YouTube. And
Mhm.
then do we want a thing about Santa Fe?
Yeah.
Okay, I'll add something
Yeah.
in about Santa Fe.
Find us at the Interplanetary Festival in Santa Fe.
Mhm.
Have we been tagged as spam already? We only sent one, Dave Shorty.
That'll do it.
Yeah, check your spam filters. Let TWIS through. Yeah. And we don't want to overdo it on what's in there, but at the same
Yeah.
time, it would be. I think that's good. It's kind of let us know. And I think maybe like, I don't know, maybe there's. I don't know. Maybe I'll think of something to just kind of throw in there as like something just to say. Write something little that can go in there.
Yeah. So it's called the Interplanetary Festival.
I think it's interplanetaryfest.org. Maybe. .com.
On June 15th,
Mm-hmm.
Santa Fe. Okay. Neat. Okay.
Hi, Stella.
All right.
Hi, Stella.
This is helpful.
Yay.
Okay. Great. So it'll be ready for you to look at pretty soon. I'll shoot you an email.
Cool. I'll try and throw something thoughtful and little together to go in there. A
Okay,
note from
int-
Kiki.
Interplanetary Fest. So I am happy to delete the bios. I just put those in there because I wasn't sure what else to do. So yeah.
No, Identity 4, I don't think you can subscribe to the newsletter and the big orange button on twist.org. I still need to put a subscribe to the newsletter button on the TWIS page. I have a window it's a pop-up window that opens. But if you
Yeah.
have pop-ups closed or pop-ups turned off in your browser, you won't see it. But flying out, if you want to email me or email Blair, I mean, Blair's in MailChimp right now. But if you want to email one of us your email address that you'd like to receive the newsletter we can put you in. We can enter you in.
Okay. How do you spell swag?
Is it SCH or SHW?
I don't know.
SCHWAG, swag. Products given away free, typically for promotional purposes.
SCHWAG? Okay.
Mhm.
Missing a C.
Bleak. Stuff we all get. Swag.
Okay. Cool. And then I need a picture.
Ow, it's an acronym.
Okay. Save image as. Oh, this is where I ran into trouble last week. Saving things.
Just got an email from you and I just got an email from someone who listens to the show. I wonder if he's watching right now. Paul Lombardi, are you out there right now?
TWIS Women in Science. That is a great subject line for an email. I can't wait to read that.
Yeah.
Okay, let's see.
Bleak. We've all been on the internet too long.
Let's see here. Okay, great. Those are my things. I could be here forever doing this stuff.
Yeah. Okay, so so Brian cannot come to Santa Fe.
No.
Marshall and Kai will be there.
Oh,
So
great.
maybe they can help a little bit.
Yeah.
And they will also have an AV person watching the sound and the recording, is what I've been told. So
Okay.
there will be someone at the stage to help us out.
Great.
Yeah. So what I just need to figure out is that make sure we've got enough microphones and a good way to put everything together. So I'm going to deal with all the tech side of things.
Yeah. Are we trying to simulcast?
I don't know. We can try, but it's not going to be my huge priority. But
Yeah. I think, well, because are we doing a normal show? We're not, right? We're interviewing a couple people, talking about planetary stuff.
Yeah, we have one interview scheduled,
Okay.
and then we'll talk about interplanetary things.
Okay.
Yeah, so it's gonna, and we have a 60-minute podcast spot. So,
Okay. So would it be appropriate for me to bring things that are a little bit older but are related to what we're talking about, I guess? That's my question.
you could, or we could do, I don't know, maybe we could come up with some kind of game to play. Like a cryptozoology game, like
Ooh, that'd be fun.
come up some, we have the interview, we could do a couple of stories, but really I'm thinking that, I mean, if we're not, the interview would probably be the bulk of our conversation.
Right.
And the rest of it, like I think will just be conversational type stuff. We can bring like a story or two a piece, but I don't know that we'll even get to them. And I think it would be more interesting maybe to use them as like jumping off points to talk about aspects related to space travel and space colonization and going to other planets and
Right. Okay.
yeah, I don't know, like maybe I don't know, maybe you could have a story about tardigrades in space, or
Oh, that would be great.
yeah.
Or how some animals use celestial bodies to know where they're going.
Yes. Yeah, how could we do that in space? Celestial bodies, pulsars, we use them. We use the pulsars for navigating. Oh, speaking of tardigrades, I absolutely forgot. Did I tell you about the book Willow the Water Bear?
No.
My gosh.
It sounds like a thing I need to know about.
Yes, you do. So, this guy who wrote this book, it's a little kid's book, Willow the Water Bear, and by Houston Kidd. There we go. That's where it is. And Houston asked me if I would if I would review the book to give him a quote for the back of the book. And so I
Really?
read the book. Yeah, I read the book and I really liked it. And so I said, water bears are amazing creatures, and this story turns real scientific information about them into a thrilling adventure that ends with an important lesson for all. It's definitely a book I will read to my own child.
Cute.
It says Dr. Kiki Sanford, scientist, host of TWIS podcast. This book is on the International Space Station now.
What?
Yes.
That's quite an honor.
This book with TWIS podcast on the back of it. It's on the International Space Station, and it's gonna be read aloud from space.
Wow. Nice.
Oh wait, did I put that up there? Yeah. Yeah.
Huh.
It's super cute, and it's a super cute book about this little Willow the water bear, and her parents take her around to find all these adventures and meet all these extreme creatures, and then she finds she has superpowers inside of herself the whole time, and she goes, yeah, she's like, "Oh, look at me, I'm in space. Look at me, I'm in this other place. Oh, look at me, I can handle all these extreme conditions."
I love that.
Yeah, it's a really cute story.
Hmm. Well, I might need to have that in my office at the zoo.
Oh, yeah.
Might be necessary. Oh my.
Yeah, you could do read aloud. You could do read aloud at the zoo.
I read stories all the time. I'm mostly with older kids, but I'll jump into the younger kid classes so I can read books to the kids. I love doing it.
Oh, I love that.
It's one of my favorite things.
What are they? Oh, they've been reading. I'm trying to figure out what is going on in the chat room conversation. Decomposing. Poo. What? I don't even know what's going on.
Who even knows?
I'm behind the chat room times.
Who even knows?
I would read aloud. Yeah, look. Oh, wait. When's it going to be read aloud? Oh, crap. I did not mean what just happened.
What did just happen?
My whole screen just resized itself. That's weird.
Oh my.
Where did you go? I lost you. What just happened? Why did it do that? My whole computer screen just resized to a massive size. I can't see anything anymore.
Oh no.
Oh my god. Noodles, I want your cookies. I like cookies. I like cookies. How do I fix this so that I can say I can't find Blair? There you are. Okay.
Hello.
Hi, you're taking up my entire screen now.
Uh-oh.
That's huge. I have a giant screen here and you're in all of it.
Oh boy.
Uh-huh. Hey,
How do
settings. What's up, settings? Why'd you decide to display funky settings?
Videos? That's not what I want. How to stop the extinction. Okay.
Is it gonna come back?
What's up?
Crap.
What's wrong?
Now it's completely broken. I can't
What's
see
wrong?
anything. Are you there?
I'm here.
Oh, it's so broken. Why aren't you listening to me, computer? I don't know why it did that, and now I'm really confused. I need this. It's because I opened up this web page. I know it. Well, then go away, web page.
What did we talk about last week?
What did we talk about last week?
Yeah. I'm trying to finish the newsletter.
You guys are everybody's telling me things in the chat room. I don't know how to read anymore.
It says, tell Kiki Windows key plus escape.
Oh, see, that's the problem. I have a Mac wireless keyboard
Oh, no.
hooked up to my Windows computer, so I can't hit that Windows key. There's no Windows key on my Mac keyboard.
That is a problem.
Oh my god. I know web pages can't force full screen. I don't know what happened. It just all of a sudden decided that it was going to go full screen.
It happens from time to time. Let's see. You said we're going to fill your head with phages, fly sex, and hot ice. So I will say that. What we talked about.
Mm-hmm. Command escape. And nothing's happening.
Phages.
Control is crap.
Fly sex and hot ice.
Oh wait, I have my settings open. I don't need to do that. I found that. I don't know why. Everything's so huge.
Sounds like a personal problem.
Oh, why? I have to fix it, right?
Okay.
Yeah, some apps
Okay.
like blurry, go away settings and other stupid computer mess up things. I think my computer wants to be restarted is what it wants.
Yeah, that's fair. It's pretty late.
Saying, hey, Kiki, I really just want to be restarted, so I'm just kind of giving you a hint here that, I'm tired, and being restarted might be kind of nice.
Okay, this is ready for you to look at.
Yay!
Okay, so yeah, take a gander and let me know what you want to do. Did somebody I didn't get an email. Flying out. Were you trying to email me to get added? Because I could do it right now. Just saying.
Dr. Hulbe just emailed and said, thank you for the invitation. That was loads of fun. She listens to the podcast on the weekends, so actually watching during work was a treat. I'm now pondering how to use mastic lumps in casual conversation.
Yeah! Oh, somebody already have my email from the calendars. Okay, so I got Bleak's. Bleak sent me a private message. Flying out, you can do that too.
Yeah,
the IRC.
Yeah, you can do that.
Bleak, I'll add you right now. Here, audience. How do I manage audience, add subscriber? That's what I want to do. Oh, Bleak, you're already on the list, so that means spam.
Yes, I think I remember adding Bleak.
Okay, great. Great.
Yeah.
Spam or was added after the Hippo newsletter?
Either of those options. It's a possibility as well.
Because we only had like 40 people on the list when I sent the Hippo letter out, and now we have over 200. So a lot of people didn't get that one, I think. Sadly.
It is sad. Get it, people. Get it. What else is going on on.
Oh, check this out. Here, I'll show and tell.
Infinity
real quick.
4, you're funny.
I'll move my camera.
What? Ooh. Did you put that together?
Oh, heck no.
That's awesome.
That is the largest Lego set ever made.
Is it larger than the Death Star?
Yeah.
Oh.
Yeah.
Awesome.
It's 7,500 pieces.
It's a lot of pieces. That's
Yeah.
many hours of attention.
Yeah.
I'm really not happy with
It's been like 2
it.
years, I think. I think it took him about 2 years. Now we
2
just
years.
have to buy a glass coffee table to put it in.
Yeah, so it's a display case, right?
Yeah.
Yeah.
Anyway.
That's awesome.
All
We
right.
need to-
Well.
we need to do more projects. I love projects like that.
Ooh.
I know. Lego envy. Tell me about it. That's one of those things that I've gone to the Lego store before and been like, I'm not buying that. That I have Lego lust, but I will not give in. I will not buy it. A
Cool.
plumbus.
Oh yeah, I do have a plumbus. It was my birthday gift to Brian. Here, let me just
Where's your plumbus?
this. It's a plumbus.
What?
Also, this is what the back looks like.
What?
It's from Rick and Morty.
Oh, okay.
It's from the second episode of Interdimensional Cable. But it came with a care manual, and I should grab it and read it. It's really good. One of the things is you can't put it near a mirror or it'll replicate. Hold on, I'm gonna grab it. Hold on. One second.
Yes, it will. Yes, it will replicate.
Where'd it go?
Oh my goodness. Oh my god.
No.
I don't know where your
I don't know. I don't know
care
where the
manual
plumbus
went.
care manual is, but plumbus owner's manual.
I'm confused about this math thing, and I'm adding and subtracting numbers inside of numbers, and
Oh, here we go.
I can see it.
Okay, let's see.
Friday, yes, Twitch stream 1:15 probably 1:15 p.m. Friday, twitch.tv/Dr. Kiki if you are interested in hanging out and chatting about science, talking about things in the world, and having a nice conversation. I would love to have your company for conversation. It'd be cool.
Oh, here we go. Plumbus is not alive, but do talk to Plumbus for CO2. Placing Plumbus near reflective surface will result in duplication. Do not operate Plumbus within 7 cetons of other Plumbuses. Regularly grooming Plumbus induces desired behavior. Keep Plumbus powder dry. Always keep an ideal temperature. Plumbus will sweat if too hot or cold. If too red, return Plumbus immediately to manufacturer, not to store. Test Plumbus on a small area before applying to larger surface. Pressing Plumbus against sensory organs will result in sickness or death. Exposing Plumbus to atmospheres greater than 8% branzine not recommended. Plumbus may cause emotional disconnect from duties. Never stare directly at the parted chumbles. Instead, poke a pinhole in sheet of paper and stare at chumbles through hole. If not cleaned regularly, Plumbus will attract dark plumbus. Plumbus may suddenly expand one size. Take necessary precautions.
I like good instructions.
Yeah, there you
That's
go.
very nice. Yes.
Never fully cover plumbus while sleeping. Always face plumbus east when praying. Always turn the grodus to desired trim length. Using plumbus in correlation with scrupulous will result in a 6.00.32 fine. If plumbus revolves faster than 200 RPM, it must be boiled. Outline of plumbus should not be traced onto paper. Don't muss up the chumble.
Don't muss up the chumble.
There you go.
That's silly.
That's plumbus care.
Don't muss the chumble.
Yeah.
I don't even know what I just said.
Yeah, do you watch Rick and Morty at all?
I have. I'm not a regular consumer.
Yeah.
Usually I've had to turn it off. Marshall thought it was appropriate for Kai to watch.
Oh, no, it's not.
Mm-mm. And I was like, okay. And then I'm like, this is not okay.
No, it's not appropriate for younger eyes.
No. Marshall's like, yeah, it's Rick and Morty. It's fine. I'm like, I don't understand what you think is okay. Like,
Yeah, it's definitely not.
we
Definitely not.
need to talk, kid. Let's talk. Yeah, not appropriate. So I've only watched like an episode here or there because usually Kai's around. And so I'm not like hanging out and watching all the shows that I would like to watch, unfortunately.
Yeah. Someday.
Someday. It's all good.
Someday. It'll be appropriate for all of you, and he won't want to watch it with you. Oh no.
Mama, I don't even want to hang out with you.
Oh man.
No, don't like that. Yeah, Pam, G-rated. I try. We tried G-rated for a very long time, and we're pushing the envelope with the Marvel movies, I think. But for the most part, we stick with PG at the highest. Well, I think maybe we started going into some PG-13, but which would be the Marvel movies. But yeah, we really try and stick to G and PG if we can. Really. My media consumption for the last 8 years has been limited. Limited
That is fair.
by opportunity. Yes. All right.
People are sending me their email addresses.
Oh, awesome. Good.
Okay.
Good.
Let's
Because
see.
they know that you have the window open right now.
Ooh. And everybody who's messaged me is already on the list.
Oh, good.
So that's great.
Yeah, I took a lot of people emailed me. Some people emailed me, and other people sent me Patreon messages, and I put people on the list. But it's good to double check.
Okay. Oh.
Yeah, Dave Shorty, you're gonna keep waiting for that 6 and 7-year-old to be ready for Rick and Morty. It's a few more years yet. Oh, I
Yeah.
love the Miyazaki films. Those are fantastic. Yes. And Bleak, you're absolutely right. And you should not have probably seen Bloodsport at a young age. Yeah, that one a little bit much. But yeah, I mean, younger kids have older siblings and get exposed to all sorts of stuff and end up totally fine.
Mhm.
all the time. It's just kind of what happened. The first kid goes through and you're like, kid gloves and take everything carefully and I'll only expose you to the nicest things. And then all of a sudden the second child comes through and it's like, whatever they're watching,
Yeah.
whatever's happening. Okay. by the, by the fifth or sixth kid, it's just like, I don't even know what's happening anymore.
Yeah.
And you
Let's
played.
hope neither of us figure that out.
No, I'm not going to. Yeah, Bleak, we know there's evidence. There's so much video games don't make people aggressive. Aggressiveness makes people aggressive. Bad home environments, possibly. Environment and genes. But video games don't necessarily make. Yeah. Yeah. All right. I like video games. They're good.
Oh my gosh, somebody else.
Get on it.
I just closed the window.
Don't close the window.
Male Kimp. Like in
Male gimp?
no, male Kimp. There's
Like male gimp, like the one that you keep in the basement?
it's so if you ever listen to Serial,
Yeah.
they had the ad for MailChimp where people were saying MailChimp wrong. That's all I can picture now when I
Okay.
it's pretty funny.
I like it.
Alrighty.
Yeah. Should we do it? Should we call it?
Yeah.
Yeah. For some
Yep.
reason, I woke up early this morning, was just like, boom, I'm awake now. Now I'm tired. It's good. Mm. All right. Everyone, thank you so much for joining us tonight. Thank you for letting us know whether you want to be on the newsletter mailing list or not. And thanks for enjoying the show. I do hope that we will see you again next week. Come back for more science, for more fun with all of us. Who knows what crazy invertebrate story Blair will find for next week's show.
Yeah, it's been a good couple of weeks.
Yeah.
Too bad we're not going to the entomological conference now.
Yeah. No, it's good. All right. It's good. All right, everybody. And Blair, thank you for a great show.
Yeah, thank you. It was a fun one.
It was fun. Everyone have a wonderful week. Have a wonderful weekend. Enjoy the science. We'll see you again next time. Thank you.